So today we are going to locate the shear center of a given open section. If you see that the side view of the beam, it is here channel section or C section. So here I have given a typical cantilever beam. So you can see here I have a long beam, one is fixed with one is fixed and other is free. Now if I cut that beam at any section, you can see the side view. So this is the side view of the given beam, given open section beam. So now to define this channel section, we need to define the geometry. So here I have given the width of the flange is, that is B is 50 mm. So from here to here it is 50 mm, and the height of the web is 75 mm. So from here to here is 75 mm. Generally, we call the horizontal member as flange and vertical member as web. So now it is a symmetrical, single symmetrical cross section. That means when I cut along the horizontal axis, I can have two symmetry. So that is why it is called a single symmetry cross section. So now we define the width of the flange, height of the web. Thickness is given. Thickness is 2 mm. Thickness of flange and web is 2 mm. So now we have defined the geometry of the cross section of the beam. So now we go to the setup. So just I have shown the schematic of that beam setup. So we have taken 2 points A and B. So this is the point where we are going to apply the load. So the idea is we are going to apply the load and we see reflection. From the reflection we will get the rotation and then we will locate the shear center. So anyway, we will go step by step. So firstly, we have defined that we are taking 2 points, that is A, B. The distance between the point A and B is 160 mm. I have shown here. So these are the points where we are going to apply the vertical load. So at point A, I am going to apply the vertical load called WA. At point B, I am going to apply the vertical load called WB. So the load which I am going to apply on the beam is WB. That is the summation of A plus B. So we are going to apply a vertical load at this point A and B. So now the main aim of this experiment is to locate the shear center of the given channel section. So this is the point, you can see. So this is the point we can guess that the shear center, because already I have mentioned the shear center will always lie on the axis of symmetry. So for this channel section, this is my axis of symmetry. Now I need to locate the correct point. So it can lie anywhere along the axis of symmetry. It can act here, it can be here, it can be anywhere. So now what I do, I take the web as a reference. So in today's lab experiment, we are going to define the shear center E, that is the shear center from the web, that is called E. So in today's lab experiment, we are going to compute the value of E. So what is the value of E, or the location of shear center from the web? So web is my reference point. So anyway, so in few minutes we will see the tabulation, how to take the readings, and we have a formula to compute that shear center for a given channel section, and then I will show how to get the shear center using a graph. So now we are going to see a theoretical formula to compute the shear center of the given channel section. So this is the formula we can derive by using shear flow of open section. So it's 3b divided by 6 plus h by b. So here the b stands for the width of the flange. For us it is 50 mm. Again 6 plus h stands for the height of the web, which is 75 mm. Again b stands for the width of the flange. So now if we know the value of b and h, then it is possible for us to compute the shear center of the given channel section. Please make a note, this formula is only for channel section. If I have some different section, then I have a different formula. So for channel section, it is possible for us to compute the shear center theoretically. So now one thing I want to convey, if you see the geometry, the schematic of the beam setup, I have told that A and B are the points where we are going to apply the load, that is W and WB. So when I apply a load, there will be deflection. So to measure deflection, we have two depth gauges which is located at the top of the beam. You can see at the top left we have D1. So this is depth gauge 1 and this is the D2 depth gauge 2. So the idea is, by using two depth gauges, it is possible for us to compute the rotation of the beam due to the applied vertical load. So we are going to see the tabulation. So I am going to explain how to get the data, that is the theta and E value experimentally. So already we have seen that the schematic of the beam setup. So we have taken the points A, B. That is the point where we are going to apply the vertical load, WA and WB. And so here you can see WA is the load applied at point A and WB is the load applied at point B. And WB is nothing but it is a total vertical load. It is equal to WA plus WB. So now already we defined that distance between A and B is 160 mm. So you can see for the first reading I am applying 2 kg at the point A and I am applying 0 kg at point. There is no load at point B. So for this set of loading, I will be getting the deflection which was noted on the top of the beam, D1 and D2. So I get some kind of 0.5 and 0.2 something I get. Similarly, I have to do it for the second set of loading. So for second set of loading, I remove 200 grams from the point A and I keep it at point B. So 1 kg at point A, 0.2 kg at point B. So I will get the deflection accordingly. So now the difference between the deflection will give the rotation in theta. Okay. So now we have got the theta value for the given set of loading. So now we need to also compute the location of shear center, that is the distance from the web to the shear center is E, that we need to compute. So we have the formula, already I have mentioned, it is AB into WA minus WB divided by 2 into WB. So all the values are known to us, just simply plug in those data and you will get the E for each set of loading. So now we have two sets of reading, that is theta and E. So now we are going to plot the graph between for theta and E. From the graph, we are going to find out the shear center of the given open channel section. Just now we have seen we have calculated theta and E. Right? Theta is rotation and E is the distance between the web and the shear center. So now we need to find out the shear center of the given open channel section. So already we have a set of data theta and E. So just to plot the graph theta versus E. So now if you plot the points from the tabulation theta and E, you get a nice linear curve. So now we need to identify the location of the center of the given channel section. So we all know that in the beginning I have mentioned that shear center is a point where I have bending without twisting. That means there is zero rotation. So now you can observe closely the graph. So this is the point. This is the point where I have zero rotation. That is theta is 0. So this point is called the shear center of the channel section. So from here it is around roughly 20 mm. So you can, if you plot the graph, you will get this value. So by this way, it is possible for us to compute the location of shear center of a given open channel section. So now we have computed the shear center experimentally, it is 20 mm. We can also compute the shear center theoretically. So already I have shown the formula. When we know the values of the width of the flange and the height of the web, then it is possible for us to compute the shear center of the given channel section. So here, if you apply the value, I get 20 mm. So we know the width of the flange is, I think, 50 mm, and we know the height of the web is 75 mm. So for this geometry, for this dimension, the shear center of this transaction is 20 mm. So by this way, we can determine the shear center of the channel section both experimentally and theoretically.
Here we have an experimental setup for finding shear center for an open section. Here we have a C section. The C section has 2 mm thickness, and then this is about 5 centimeter and this is about 7.5 centimeter. We have 2 dial gauges on 2 ends. We will be having weight hangers, and we will be placing weights on one side, and then we will start measuring the displacements on these 2 points. We will be transferring weight from one hook to another hook, such that we will be noting what's the difference between this D1 and D2, and we will be plotting this D1, D2 which will be in terms of the twist angle theta, and then we will calculate E from that. We will plot E versus theta, and from that we will be able to determine where the shear center is. So most probably for an open section like this, we might find shear center outside the section. So to use this setup, we will need 2 dial gauges, 2 weight hangers or hooks, and then a set of dead weights. So to dismantle this setup, we need to remove this dial gauges, and then need to remove this weight hangers. First we will place the weight hook. We will place the dial gauges. I have to use the magnetic stand to fix the dial gauge on the platform. And then set the dial gauge to 0. And start adding weights to one of the hooks. Let us number it as 1. Next we need to transfer weight from one hook to another hook for experiments. Then you need to note the dial for what's the displacement. After transferring all the weights, we can unload the same.